Before a transformer model can do any of its incredibly clever attention math, it has to tackle a massive, fundamental hurdle. It has to take human language and somehow turn it into mathematics. So we're going to focus entirely on that absolutely crucial first step where text gets transformed into lists of numbers, a process known as input embedding.
Think about it. A neural network is basically just a giant mathematical engine, right? It only does arithmetic on numbers. It absolutely cannot process text. If you feed it the word king, the model literally has no idea what those letters mean. It doesn't have a biological brain to interpret vocabulary. So before any actual processing or understanding can happen, we have to turn every single word into numbers. But as you'll see, exactly how we choose to represent those words as numbers makes all the difference in the world.
A naive, most straightforward first attempt at solving this translation from text to math is a technique called one-hot encoding. Let's define what that is. One-hot encoding represents each word as a vector, which is essentially just a list of numbers that is the exact size of your entire known vocabulary. Say your model knows 37,000 words. In one-hot encoding, every single word is represented by a list with 37,000 slots. To identify a specific word, you fill that massive list with all zeros except for a single one placed in the exact slot assigned to that word. So the word king might just be a 1 in position 4,271 with 36,999 zeros everywhere else. It's a very blunt way to say, this is word number 4,271. But we run into major issues with this approach almost immediately. One-hot encoding has two fatal flaws. First off, it's huge and it's completely sparse. You're forcing the model to compute using massive vectors that are almost entirely zeros. Second, and far more importantly, one-hot encoding carries absolutely no meaning. It acts exactly like a random unique ID number. Under a one-hot system, every single word sits the exact same mathematical distance from every other word. Because they're just unique slots, the word king is mathematically no closer to the word queen than it is to the word armchair. And that is a terrible starting point for a model whose entire purpose is to understand the contexts and relationships between words. What we want instead is a dense embedding. A dense embedding replaces that massive, sparse list with a much shorter, dense vector of real numbers. And crucially, in a dense embedding, those numbers actually reflect something about the word's attributes, allowing similar words to mathematically land near each other.
To put the sheer scale of this dense embedding layer into perspective, you have to think of it as a giant table or a massive matrix. In a foundational base model using a vocabulary of 37,000 words, the dense vector size, a dimension known technically as D model, is 512. That means this embedding layer is a matrix of 37,000 rows by 512 columns. We've got one row for every possible word and 512 numbers deeply representing that word.
So how does this actually play out in operation? How does the model use this giant matrix? Well, it's actually much simpler than you might expect. When a word comes into the layer, step 1 is receiving that word. Step 2, the layer simply finds that word's corresponding row in the matrix. And step 3, it pulls out those 512 numbers. That retrieved row is the word's embedding. There's no complex computation happening here. It's purely a retrieval operation. It's exactly like looking up a word in a dictionary or finding a name in a phone book. You aren't doing math to find the definition, you're literally just turning to the right page. Now, under the hood, mathematically speaking, this lookup is the exact equivalent of multiplying that massive one-hot vector we talked about earlier by the weight matrix. But the lookup is just a highly efficient shortcut for that multiplication. Ultimately, an entire sentence gets processed this way and simply becomes a stack of these pulled rows.
Which brings us to a pretty massive, obvious question. If we have this huge table of 37,000 rows and 512 columns, where do the actual numbers inside that table come from? We certainly aren't sitting around hand-designing 512 unique mathematical attributes for tens of thousands of individual words. So how on earth does this table get populated?
The answer lies in one specific, powerful concept: learned embeddings. This means the embedding table doesn't start out with deep linguistic knowledge. It actually starts out filled with essentially random numbers. But during the training process, those numbers get continuously adjusted, just like every other weight in the neural network, so they better represent the words for the task at hand. The embedding table is an active part of the model's parameters. Think of it like a brand new employee who starts on day one knowing absolutely nothing about the company. But by doing the job day after day, they slowly build a detailed mental map of how everyone and everything relates. The model is discovering its own unique mathematical representation of word meaning directly from the data, rather than being explicitly told what to do by human programmers.
To really grasp the power of allowing a model to learn its own semantic map like this, we can look at a famous piece of intuition from earlier word embedding research. Before transformers even existed, an embedding method called word-to-vec proved that when vectors are learned from data, semantically related words naturally group together in mathematical space. The classic demonstration of this is geometric arithmetic. If you take the learned vector for king, subtract the vector for man, and add the vector for woman, the resulting coordinates land incredibly close to the learned vector for queen. Now, I want to be clear, this specific king and queen arithmetic is a well-known result from word2vec, not a specific feature hard-coded into the transformer architecture itself. But it's the perfect standard illustration of what learned dense embeddings can achieve. It shows the intuition behind the whole concept. Similar words and relational concepts naturally map to similar mathematical vectors.
Now let's dive into a couple of specific, critical details about this pipeline that usually get glossed over. You can't just take raw text and look it up in a matrix. There's an essential step right before the embedding lookup. First, you have the text. Second, that text must be mapped to numeric token IDs using a fixed vocabulary built from the training data. Only then, in step 3, do you use those numeric IDs to retrieve the embedding vectors via the lookup table. It's exactly like a coat check at a restaurant. You can't just walk behind the counter and grab your coat, which is our vector. First, you have to exchange your raw text for a specific ticket number, the token ID. Only with that ticket can you actually complete the lookup.
And because of that critical step, we need to clearly define what a token actually is. A token is a unit of text mapped to a numeric ID. But crucially, a token is not always a whole, complete word. For instance, in an English-to-German translation task, a technique called byte-pair encoding is often used to create a shared vocabulary of about 37,000 tokens, and a lot of those tokens are subword pieces. So while we often simplify things for the sake of conversation by saying one word becomes one vector, in reality, the precise term is token, and a single complex word might actually be broken down into multiple subword tokens before being mapped to IDs.
The second architectural detail you need to know happens immediately after the lookup. Once the model retrieves those 512 numbers for a token, it doesn't just pass them along as is. These looked up weights are actually multiplied by the square root of D model. Because our D model is 512, the square root is roughly 22.6. This means every single embedding vector gets scaled up by a factor of 22.6 right before moving to the next stage. The practical effect here is simply scaling the embedding values up, but it's an important fixed mathematical step in the pipeline that you definitely need to be aware of.
There's also this fascinating piece of architectural efficiency at play here. That massive table of 37,000 rows we've been talking about, it actually does triple duty. The exact same learned weight matrix is shared across 3 completely different parts of the model. It serves as the input embedding layer we are detailing right now, it serves as the output embedding layer over on the decoder side, and it is also used as the final pre-softmax linear layer at the very end of the model. It's just one brilliantly trained table serving 3 distinct, absolutely critical uses.
So to summarize our pipeline so far, raw text gets broken into tokens, those tokens map to IDs via a fixed vocabulary, and those IDs act as an index to pull dense, meaning-rich vectors of 512 numbers out of a learned table, which are then scaled up. We have successfully turned words into deep mathematical meaning. But look at this final question. The embedding for the word king is the exact same row of numbers, whether it's the very first word in a sentence or the very last word. Our elegant lookup table fundamentally does not know, and honestly doesn't care, about position. We've captured meaning, sure, but we've completely lost order. And if human language relies entirely on the order of words to make any sense at all, how can this mathematical model possibly understand a sentence if all the words are just floating out there without any sequence?